So, in chapter 6, we're going to talk about linear transformations. And linear transformations has a set of criteria that goes with it, kind of like vector spaces and stuff like that. But before we jump in, I want to start by talking about some terminology that we need to understand in this chapter. Some of it we've heard before, like domain and range. So let's get started. A standard function terminology is going to be used with these functions. So V is called the domain of T and W is called the codomain of T. So if little v is in V and little w is in W, such that T of V is equal to W, this is talking about a linear transformation is happening. And it's going to take us from this world V into this world W. Then W is called the image of V under the linear transformation T. They're using T here to signify linear transformation. That's common in most linear textbooks, and that's the terminology that's going to be used in this textbook. The set of all images of vectors in V is called the range of T, and the set of little v in V, such that T of V is equal to W, is called the preimage of W. Now, what does all that mean? So let's start by looking at a picture here. So we have this world that V lives in. And that's the domain. Those are the types of things you can plug in to this function. And we can think about transformations kind of like functions in a way. And when we apply this transformation to it, it's going to transpose us to another world. Okay? Where these are the possible things that could have come out. That's your codomain. However, what did come out was this little section in here, and that's called the range. So when we talk about that image, the image is what the vector looks like when I apply the transformation rule to it. The pre-image is, suppose I start with W, well, what did it look like back here in this world? What would that original vector have been? So let's define those things. These are not technical definitions, but this kind of gives you an idea of what you need to understand in a sense for what these mean. So domain. The domain's always what goes in. Even when we talk about a regular function, what kind of things can I plug into a function? Let's say we have f of x is equal to x squared. Well, what can I plug in? Well, I can then plug in all real numbers. I want you to think about the codomain. I'm going to abbreviate it that way. As what could possibly come out of this? Well, if I'm plugging all real numbers in, I could get all real numbers out. Okay? Except I don't get all of the real numbers out. I get a small subset of the real numbers out. Specifically, if I'm looking at this guy in terms of domain, codomain, and range, what I'm getting out is actually all the real numbers that are greater than or equal to 0. I'll say it like this. So I want you to think about those kind of that way. Domain and range are same ideas, pretty much same definitions that you would have back in an algebra course. But now codomain is something that's a little bit new for us because we don't really think about codomains with functions. But we do need to consider that a little bit with transformations because we may be going from R2 to R3 if we have a transformation that's designed to do that, but we may not get all of R3 out. We may only get a small subset of R3 out. So that codomain is, in a sense, what could possibly come out of this, but the range is what actually comes out of that, and that's what's going to give us that mapping back and forth. We could even create, suppose we had a table that looked like this. And we had a mapping here. And I asked you to identify the domain and the codomain and the range. So the domain is what kind of numbers are going in. So here, these items are heading this way. We know that by the arrows. So the domain would consist of the numbers 1, 2, 3, 4. The codomain, what could you possibly get out? Well, in this giant set over here, everything's mapping to these numbers. So it's the numbers 1 through 6. But we're not hitting all of those numbers. The range is what you're actually getting out. And in this case, the range would consist of the numbers 2 through 5. So it's like, I have this world here with these items. There's my domain. It's going over to this world that consists of these items, but I'm not hitting all of those items. These 4 just map to here. So there's my transformation that gets us from point A to point B. But this guy is the range. This big one is the codomain. Whereas this guy is the domain. These are the things I'm plugging into some function. It's just a very generic example here. And these are the guys that's coming out. But these are the possibilities. I just don't happen to have something that would give me 1 that lives in this world. I don't happen to have something that would give me 6 that lives in that world, and so on. Now, when we talk about the definition of image and pre-image, I want you to think about the image as, if I apply this transformation rule, what does the vector look like under that rule? The pre-image is what it looked like before. So what did it look like before I got to this new world? Now, let's look at a few examples to make those things a little bit more concrete. In problem 2, we want to look at image and pre-image. So this guy is a transformation. We'll talk about how to prove it's a transformation a little bit later. We want to know, what is the image of V? So we want to find the image of V, and V is the vector 0, 6. Well, under this transformation, I'm taking something that's in R2 and I'm going to something that's in R3. So that first component is going to be 2 times R2 minus, 2 times V2 minus V1. And then I'm going to have V1 for the second component and V2 for the third. So my vector 0, 6 is going to the vector 12, 0, 6. So this would be the image of V under the transformation T. This is what it looks like when it goes from R2 to R3. Now B is asking you to find the pre-image. So in other words, what did you have to plug in here to get this guy out? So we have 2V1 minus, So our vector 3, 1, 2, okay, that's where we went to. We're asking, where did we start from? Has to follow this rule. So 2V2 minus V1, V1, and then V2. So this is going to give us a system of equations that we're going to be able to solve. So 3 is going to be equal to 2V2 minus V1. 1 is equal to V1. 2 is equal to V2. So this is nice, but we have to verify it's going to work in here. And it does. 4 minus 1 gives us 3. So then our pre-image is going to be the vector 1, 2. So the vector 1, 2 is in here, and it maps to the vector 3, 1, 2. Well, let's look at 6. Well, before 6, let's talk about domain and codomain for 2. So domain is what you're plugging in. We kind of talked about this with the picture up here. We were plugging in things from R2. Our codomain, what are we getting out? We're getting out things from R3. And then remember, the range would be what specifically am I getting out. And that's going to go a little bit further in depth. But I think you can map most things in R3. Now let's look at 6. I'm just going to recopy that. So V is 2, 1, 4. W is negative 1, 2. A is asking us for the image of V under T. So if we plug this in, what does that look like? That's what that's asking. So we're going to have 2 times 2 plus V2, and then V2 minus V1. So we're going to get 5, negative 1. Oh, be careful with V1 minus V2 here. So V1 is 2, V2 is 1. So that's going to give us a positive 1. So there's your image. If we were to apply this transformation to this vector, we get out 5, 1. B is asking for the pre-image of W. So in other words, how do we get out the negative 1, 2? So let's set up that system of equations. There we go. So we have 2V1 plus V2 is equal to negative 1. V1 minus V2 is equal to 2. And we're going to do some REF here. And I got 1/3, negative 5/3. So you have to be careful with this one. Here we had a 3-dimensional vector going to 2-dimensional space. So our domain is R3. The codomain, what I'm getting out, is going to be R2. So that means the pre-image has to be in 3 dimensions. Well, when we set up this system of equations, we ended up with stuff just in 2 variables, V1 and V2, and that was because of the way that transformation was defined here. Notice it didn't use V3 at all, which means that in that pre-image, it doesn't matter what V3 is. It can be anything as long as it's a real number. We will still get something that maps to this vector, which means that there's an infinite number of vectors here that will map to this vector negative 1, 2. And that's all because of the way this guy has been defined. It's not taking that V3, that third component of that domain vector into account. So there's our pre-image. So let's talk about the definition of a linear transformation. What is a linear transformation anyway? So we're going to start with vector spaces v and w. So the function t from v to w, from vector space v to vector space w. So we're going from one vector space to another vector space. It's called a linear transformation of v into w when it has two properties that are true for all vectors u and v in vector v and for any scalar c. So the transformation of the sum, u plus v, has to be equivalent to the transformation of u plus the transformation of v. And then the transformation of the scalar c times u has to be equivalent to the transformation of u multiplied by the scalar. So we've got to check two properties to see whether or not we're going to have a linear transformation. So let's look at a few examples. So we want to show that this is a linear transformation from R2 into R2. So I'm going to do that on the next page. So we want to prove this guy's a linear transformation. So we're going to start with a couple of generic vectors, u and v. And we're going to let c be a scalar. So notice if I add u plus v together, I get u1 plus v1, u2 plus v2. So we're assuming, like we said before, standard definitions of addition and scalar multiplication unless otherwise defined. So let's look at those two axioms. T of u plus v has to equal T of u plus T of v. So I'm going to start with T of u plus v. So that would be the transformation of that sum. And that transformation under this says it's going to be v1 minus v2. So first component minus second component. So first component minus second component. And then it's going to be first component plus 2 times second. First plus 2 times second. So I've got u1 plus v1 minus u2 minus v2. And then I've got u1 plus v1 plus 2u2 plus 2v2. So I'm going to do some rearranging here. So I rearranged so that I had the u and the v stuff kind of grouped together here. And couldn't I rewrite this as the sum of two vectors? And then if we look closely, this guy actually is the transformation of u. And this guy actually is the transformation of v. So we were able to go from this to this pretty easily. Remember, the other way to prove things is that you could start with this guy, kind of simplify, get here, start with this guy, which would take you there, and which would take you there, and show that they're equivalent. But this one was nice that we could easily go from one to the other. So now let's look at that second axiom. This is what we're trying to prove. So if we were to look at Cu, that would be the transformation of Cu1, Cu2. And our rule says that it's first component minus second component, and then first component plus 2 times second. So we could factor a c out of those two terms, and factor a c out of those two terms. So then couldn't we pull the c out? And then u1 minus u2 here, u1 plus 2u2. Because that's the same thing as distributing each one in, which would go back there. This guy is our transformation of u. So we have proven that t of cu is equal to ct of u. So we would say, yes, this guy is definitely a linear transformation. So let's look at another one. What about 9? Is this guy going to be a linear transformation? So we're going from R2 to R2, and this guy's going to map, no matter what x and y are, to x, and that y coordinate's always going to be 1. So let's look at this guy. So the transformation of u plus v. So that would be u1 plus, we need to take the transformation of u1 plus v1, u2 plus v2. So notice we have not applied the transformation yet. That's what that t means. And once we apply it, then the t goes away. So this transformation says that first component stays the same. There's our first component. Second component maps to 1. So now let's look at tu plus tv. So the transformation of u1, u2 plus the transformation of v1, v2. So that would be u1, 1 plus v1, 1, which would be u1 plus v1, and then we would get 2. But there's a problem, right? Because this isn't in that form. We have something completely different here. We're supposed to get a 1, we end up getting a 2. This just has all kind of problems, which means no, this is not a transformation. Now the scalar multiple is going to fail also. So if I look at, let's look at t of cu first. That would be t of cu1, cu2. And that would map to first component, and then the second component's 1. But if I look at c of tu, this transformation would go to u1 and 1. But when I distribute that scalar, notice I'm not going to get the same thing as what I had above. Again, that second component's the issue there. So we would say, no, that guy's not a linear transformation. Let's look at that next one. We're going from R3 to R3. So we're going from R3 to R3. Let's pick 2 generic vectors in R3. And then a scalar value. I'm just going to use c. So t of u plus v. So transformation of u1 plus v1, u2 plus v2, u3 plus v3. So this says first component plus second component. First component minus second component. And then third component. So let's see if we can try to do some distributing and regrouping. So if I were to group all the U stuff together, so this is T of U1 plus U2, so first component plus second component, first component minus second component, and then third component. So that is the transformation of U. This guy is the transformation of V, because it would be first plus second component, first minus second component, and third component. So that first property holds. So now let's check our scalar property. So I've recopied it over here. Now we need to look at T of CU. So the transformation of CU1, CU2, CU3. Under this transformation, we would have CU1 plus CU2, first component plus second component, CU1 minus CU2, and then third component, which is CU3. So we could view it this way. And then we could pull that C out. So is this the transformation of U? And the answer is yes, that is. Because it is the first component plus the second. First minus second and third, which is exactly what the rule says. So we would say, yes, this guy is definitely a linear transformation. And then let's look at that last one, 17. So we are going from matrix M22 to the real. It's going to do that from matrix ABCD by adding A plus B minus C plus D. I'm just going to recopy the problem. So let's come up with two matrices that are 2 by 2s. Let's do A11, A12, A21, and A22. And B11, B12, B21, B22. And then we can use C for a scalar since we haven't used C inside that matrix. So remember what this rule is saying. So let's look at the transformation of A plus B. So it would be the transformation of, I'm going to go ahead and add those together. So A plus B minus C plus D. So it's this plus this minus this plus this. So we got to do the same thing on this. So it's this plus this minus this plus that last one. So let's kind of regroup things. Anything that belongs in matrix A, let's put it together. Anything that belongs in matrix B, let's do that and put those together. And we can do that because these are row numbers, so they're commutative and associative. So we can group those and group those. So that would be the transformation of A. This guy is the transformation of B. It's the first component plus the second minus the third plus the fourth. First plus second minus third plus the fourth, going across the rows. So this is a, it does pass the first part of linear transformation. Now let's see if it passes that second axiom, TSCA. So we need to apply the transformation to CA11, CA12, CA21, CA22. So the transformation says first plus second minus third plus fourth. And we could pull a C out. The question is this the transformation of A? And it is. So it does pass both axioms, therefore this is a linear transformation. So we've looked at several examples that are linear transformations. Now I want to talk about two simple linear transformations, and they are the zero transformation and the identity transformation. So the zero transformation will take any vector and it maps it to 0. If we were to look at something like that, it could look this way. And this guy will pass both of the axioms. I'll leave it to you to verify that. But that's what the zero transformation is it just takes everything and it just maps it to the 0 vector. So it's not a very exciting transformation, but it is a linear transformation just because it does pass both of those axioms required for that. And then the last one that's easy is the identity transformation. And that takes a vector that's in a vector space and it maps it to itself for every vector in that vector space. So it could look something like this. I'm just going to stay in R2 just for fun. So it would take the vector xy and it would map it to the vector xy. Once again, it's not a very exciting transformation, but it does meet the criteria. Therefore, it is a linear transformation. I'll leave it to you to verify that one as well. So those aren't as exciting as the other ones that we did, but they do satisfy the axioms there.